All right, good morning, everyone. Just a few reminders. Project 3 is out now. I know some of you have already started working on it. So please just pick a 2-day window that works for you and try to have it in by Tuesday. If you need more time than that, just let me know. But that is a real deadline that you should try to meet unless you talk to me about an extension. Lab 11 is out today, and if you after today's lecture, you should have the background to be able to complete the lab. And then there's also homework 10 that's due on Tuesday. Again, that deadline is flexible if you need a little bit more time. Okay. All right. So we've spent the last about month maybe talking about a bunch of different classical statistical tests. So t-tests, chi-square tests, ANOVAs, rank tests, all the things that you're using on Project 3. And so now we're going to take a step back a little bit. The next few lectures are going to be just about some more general concepts and ideas in statistics that apply to all of these tests and also to other tests we haven't talked about as well. So yes, the next few weeks is going to be talking more about these general concepts about the ways we should be using these tests and the way we should be interpreting them. Okay, so we're going to start with a quick demo. So let me move my camera here. I'm just going to point it down at the desk. Let me see if I can set this up right. Okay. All right. So I have two dice here, and what I'm going to do is I'm going to try to convince you that I have some way of predicting how these dice are going to roll. Right? I'm going to make some hypothesis about what this die on the left and what this die on the right is going to show. And the null model here is that I'm just guessing, and I don't really know the answer. Right? And so if I'm able to get this right, the p-value, the chance that I would get this right just under the null hypothesis is 1 out of 36, right, which is less than our usual 0.05 threshold, right? So if my hypothesis matches the data that we see, then that's a significant p-value, right? And we should reject the null hypothesis that I'm just making this up, right? So, all right, so let's go ahead here. So I'm going to roll these dice. Okay, so what we got here was first we got a 4, and then we got a 1. And okay, so here's my hypothesis. My hypothesis is that this one is a 4 and this one is a 1. So that probably didn't seem that convincing, right? I mean, my hypothesis is here and it matches the data really well, right, with a good p-value. But that wasn't that impressive, right? Because basically I just looked at the data and then I created a hypothesis that matched the data really well, right? And so what I just did is called harking, meaning I'm hypothesizing after the results are known, right? I first looked at my data and generated a hypothesis based on my data, and then I did a statistics test to test whether my hypothesis matched my data, and the answer is that it did really well, right? And I got a small p-value. And so, right, in this scenario with the dice, it was really obvious that that was kind of a stupid thing to do. But the problem is that often in a real science paper, we only see this sort of second part, right? We see the match between the hypothesis and the data looks really good. And right, it might just be that they didn't tell us that they had really created this hypothesis from this data, right? So what I just did obviously was not convincing, right? My hypothesis is a good match to the data, but it's because I got to see the data first, right? So that's not that impressive. Okay, so let's do something else here. So now I'm going to try to be a little more convincing. So what I'm going to do is I've got some paper here. I'm going to write down my guess before I roll the dice. Okay, so let's see. I'll just hide it over here. Okay, so now I've got my guesses, and I'll just here are the guesses that I wrote. I'm just going to stick them down on my lap here. Okay, so Let's try this again. Okay, that wasn't really a very good roll. They only just like came right out of my hand and didn't actually roll. So let's try that again. Yeah, that one also wasn't that great. This one has a little bit of dirt on it. Wait, okay, let's try this again. Okay, yeah, this one actually like did a bit of a bounce, which was kind of weird. I wasn't really expecting that. So okay, so now I got 2 good rolls, and I'm gonna pull out my hypotheses I wrote down, and look at that, right? I didn't write them down after I rolled, right? But right, that also probably wasn't that impressive. And the reason it wasn't is because I just kept re-rolling the dice until I got something that I wanted, right? I came up with excuses for why I didn't like the rolls, right? They didn't really, they didn't really work that way. I thought, okay, that one didn't really roll right. Maybe that one was a little dirty, right? I mean, maybe I could have even believed the explanations I was saying, right? But the point was that I got to try a bunch of times. And so this kind of this way to get an invalid p-value is referred to as a file drawer problem or a data peeking problem, meaning that we did properly select one hypothesis ahead of time, but then we applied that hypothesis to many different data sets, and we only reported we're only reporting the data set that actually worked, right? And so this is called a file drawer problem, meaning that there's lots of data sets that we sort of put in the file drawer and didn't tell people, right? Or a data peeking problem is another version of this that we'll talk about, where we're kind of monitoring our data set until it looks good and matches our hypothesis. Okay, so that also didn't work. So, all right, so let's try this again. I'm gonna write down my hypothesis ahead of time. So here's my papers here. I'm gonna write something down. Okay, I'm gonna put down the pen here so that there's no cheating going on. And I'm just gonna roll it one time, and we're gonna see if the things that I wrote work or not, okay? Okay, so we got a 4 on the right and a 3 on the left, right? And now I'm gonna pull out my the things I wrote down before, and let's see. Look at that match. Right, so there I only rolled once, so I wasn't doing any file drawer nonsense. I didn't write anything down after the trial started, right? So I wasn't harking, but I was still cheating, and you can maybe figure out why, which is that ahead of time before class, I wrote down many possible hypotheses here, right, which I all had underneath the table. So this kind of problem, this is actually like the most common kind of cheating, which is referred to as a multiple comparisons problem, which is that we do have just one data set, which is good, but we have lots of hypotheses that right, and we're testing lots of hypotheses on this data, and then it turns out that some of them look really good and are a good match, right? And that's also not a valid way to get a p-value, and so a lot of the class will be today I'll be talking about how to deal with this issue. So what we really want to be doing, right, is we want a single hypothesis that we pick ahead of time that is not based on this data set. It could be based on other data in the past, but just not this one. We have a single hypothesis that we decide ahead of time. We collect one data set, and then we test our hypothesis against that data set, right? That's the way to get a valid p-value. Okay. So let me switch my camera over here. All right. Okay, so we're gonna spend a lot of the class focusing on this issue, this multiple comparisons issue, which is where we have we're testing lots of hypotheses on the same data set. And so this is testing lots of different kinds of hypotheses is obviously not a bad thing to do science-wise. That's sort of the way that we build new knowledge in science. The problem is that this is not a good way to do statistics, meaning that if we do a search over many possible hypotheses and only present the p-values from significant tests, it'll almost always be possible to get a false positive, meaning even if there's nothing in the data, we could find some hypothesis that gives us a good p-value. And there's a bunch of quotes about this, about things like if you torture the data enough, nature will always confess, right? There's always some way to pull a positive result out of any data set. Back on the first day of class, I gave another example of this, right? That if we look at the presidents of the US and we look at their birthdays, there's two presidents that have the same birthday of November 2nd. And the chance of having even one president with a November 2nd birthday is pretty low. The chance of having two with a November 2nd birthday is like ridiculously small, right? And the question is, does this tell us something, right? The p-value here, the chance of getting two presidents with a November 2nd birthday is so tiny. Does that mean that there's some way that the presidents are getting chosen based on their birthdays, maybe? The problem here is that this is a multiple comparisons problem, right? That I didn't just check for November 2nd birthdays. I also checked for November 1st birthdays and November 3rd birthdays and November 4th birthdays, right? In every single day of the year. And so the chance that at least there'll be at least one shared birthday among the presidents is actually like very high. So in any group of 45 people that are randomly chosen, it's almost a certainty that two of them are going to have the same birthday, right? It's just because there's many possible days of the year. So we basically get to try like 365 of these different hypotheses. Now, if before I had seen the president's birthdays, if I had selected November 2nd and just checked November 2nd, then this would be interesting, right? If I, without seeing the president's birthdays, had somehow come up with November 2nd, right, and from some kind of model, then the fact that it's true in this data set would be really interesting, right? But since I also tried all these other hypotheses, the fact that this one worked is not that interesting, right? So this is a kind of central point of the multiple comparisons problem, is that just seeing this one significant test doesn't tell you whether that p-value is valid or not. You also need to know what are all of the other hypotheses that people tried. There's an XKCD comic about this too, which I think illustrates it well. Right, they have scientists looking for links between different colors of jelly beans and acne. So they're looking at people that are maybe eating different kinds of jelly beans, different colors of jelly beans, and they're doing lots and lots of hypothesis tests for every possible color of jelly beans to acne. And we see most of the p-values they're getting are above 0.05. But then it happens that during the green jelly bean test, they actually do get a small p-value, right? And the idea is that this is basically the study that gets all the interesting attention, and right, then you get headlines like, right, there's a significant result here, right? There's only a 5% chance of coincidence, which is also not the right way to interpret a p-value anyway. But so right, the idea here is that if you only saw this single green jelly bean experiment, this might look interesting, right? This is a significant p-value, but in fact, this is almost certainly a false positive, right? They tested if for a p-value threshold of 0.05, we'd expect about 5% of our results to be false positives, and right, so here if we run 20 tests, we'd probably expect about one to be true just by chance. So this became a big focus in psychology, primarily due to the set of studies by Daryl Bem. This is about 10 years ago or so that these studies were published. And so there's a lot of controversy over these sets of studies, which I won't have time to get into all of it. But essentially, this is a psychologist that was interested in parapsychology, and specifically about whether people could predict the identities of cards that they hadn't seen yet, or predict the identities of pictures that hadn't come up onto the screen yet. And so so he was able to get a number of significant p-values from these studies, and then right, so that led to a lot of questions about why, right? That at least most people in the psychology community thought that this was not a possible thing people could do. But the kind of techniques that Daryl Bem was using were kind of the standard ones in psychology, which was things like trying a bunch of different hypotheses, trying different subsets of your data, things like that. And so the fact that using these kinds of these techniques, these statistical techniques that were standard in the field, he was able to get this result, was one of the main causes of this replication crisis event that happened in psychology and is still ongoing in some ways today, which is that this sort of showed that the ways that we're researching things, it's very possible to get false positives, right? That even someone that's studying an effect that we think is impossible to achieve, right, they're still able to get good p-values. And so if that's true, then what confidence do we have in all of the other studies that we're running, right? We're using these same kinds of statistical approaches. How do we know that we're not getting false positives for all of our stuff also? Another piece of this controversy, which is this is a separate group, but there's this researcher named Brian Wansink, who is a food science researcher who was quite famous. And in November 2016, he posted a blog post, which was titled "The Grad Student Who Never Said No." And the intent of this blog post was to praise one of his graduate students for all the hard work that she had done. And the blog post talked about things like, when she arrived, I gave her a data set full of this study that had null results. And I said, this cost us a lot of time and our own money. There has to be something we could salvage here. Here's our plan A analysis didn't work, but here's plan B, C, D analyses. And every day she would try to run these, and we would scratch our heads and ask why, because the results didn't really make sense, and come up with another way to reanalyze the data. And then we were able to get a paper out of it, and a second paper, and a third paper, by doing this kind of digging in the data. And so people went after reading this. Many people had had the reaction of reading this that this sounds like not the right way to be doing statistics, right? This sounds like doing a lot of this kind of repeated testing. And one term for this whole category of things, of kind of approaches where people are using these invalid statistical approaches, is called p-hacking, right? The idea here is that this grad student, at Brian Wansink's request, was sort of hacking away at the data, trying to find significant p-values by running as many hypotheses as possible. So this led to a bit of a scandal. There was a big investigation. A bunch of emails got released, which you could see online. So, for example, there's emails with Brian's correspondence with his students saying things like, think of all the different ways you could cut the data and analyze subsets of it. So maybe if we don't see an overall effect, maybe we could look for an effect just in males or just in females or just people that are coming to lunch or dinner. A lot of these studies were basically things like, how do people decide how much food to eat? Are there ways we can encourage people to make healthier eating choices, things like that? So his work had a lot of practical impact on, for example, like government policies on things of trying to make people eat healthier. And so they're doing things like subsetting the data, so running tests on just pieces of individual participants, looking at different dependent variables. So in addition to measuring the number of pieces of pizza people are eating, they're also measuring how many trips did they make to the buffet, did they get dessert, did they order a drink, things like that, right? And so there's many different hypotheses to test here on different dependent variables that are all sort of about eating choices. And then, there's also in these emails, you can definitely see the pressure that people in the lab are under to try to produce positive results, right? Says things like, it's important for you to try as many things as possible before you come. It'll make a good impression. You'll get something publishable. Work hard and squeeze some blood out of this rock. So in the fallout from this, a very large number of papers from this lab were retracted. I think this is actually even an outdated list of how many things were retracted. That basically, when people went back into the data, it was clear that for a lot of these data sets, there were the statistical techniques that were used to analyze them really didn't lead to robust results. There were other problems in this work as well. It wasn't just multiple comparisons issues. There were also issues with how the data was reported. There's lots of weird stuff where data got copied between different papers and stuff. But the issue we're talking about today is this multiple comparisons issue, right? That you're almost guaranteed to be able to find a positive result if you try many, many different hypotheses. Another paper that's sometimes brought up in this context, especially in neuroimaging, was this paper in which they put a salmon in the fMRI scanner and they had it do a mentalizing. They basically ran one of their tests on the salmon that they usually run on people, where they show people that they're showing social situations, and then they're telling the salmon try to imagine the emotion that the person is feeling, and then they're using these sort of standard fMRI models to try to figure out, is there some region in the salmon's brain that's increasing for particular emotions. And they found that there was. So they found part of this salmon's brain that increased for a particular emotion. And so this by itself might make you think maybe salmon can actually tell something about social situations. But this was actually a joke paper. This was a post-mortem Atlantic salmon, meaning that this was a dead salmon in the scanner. And so presumably it's not having any brain responses to anything. Right, what's happening here is this is just sort of a demonstration that if you use a standard neuroimaging pipeline and don't properly correct for multiple comparisons, meaning that you test some hypothesis in every single location in the brain, it's pretty easy to get false positives like this. Right, this really wasn't a direct criticism of things people were actually doing. I mean, almost all, especially nowadays, neuroimaging studies properly correct for multiple comparisons, and we'll talk today about some ways that people do that. This is just showing that if you don't use multiple comparisons corrections, if you just blindly apply a hypothesis test to every location in the brain, then it's very easy to get false positives, right? Even in this case where we know that there can't be anything real. There's a question in the chat about trying to figure out from a paper whether someone did multiple comparisons, and it's very difficult to tell. So I'll talk a little later in the lecture about some ways that we could try to protect against this. But yeah, the problem is that if someone does a lot of hypothesis tests and then only reports the significant ones, there's really no way for us to know what's the other stuff they did, right? And that's one reason why this is was a large problem in the field, is that just from reading someone's paper, it's actually really hard to evaluate this. And so there are some ways we can try to deal with this. Most of them are basically things like in my demo, where we force people to write down hypotheses ahead of time in a time-stamped way. But those are really, just sort of more recent things that the field has been experimenting with. So yeah, just another note on this section here is that this is by Tal Yarkoni. He's written a bunch about these statistical issues, and just is bringing up the point that each of these kinds of hacks individually is maybe not so bad. Things like, peeking at the data, or using a one-tailed test after looking at your data, or constructing your dependent measures on the fly, things like that. The problem is that if you're using all of these kinds of fudges, it's actually quite easy to get a false positive result. So the 538 website also made a fun little demonstration of this, which is kind of interesting to play with, which is that basically they're saying, let's say we want to try to prove a hypothesis about Democrats or Republicans in the United States being better for the economy, right? And the idea here is that the statement I just said of let's say the Democrats are better for the economy, right? When Democrats are in power, the economy is better. The problem is that statement is quite vague, right? What does it mean for Democrats to be in power? How do we want to judge? Does that mean like when there's a Democratic president? Does that mean when there's lots of Democratic representatives or governors? And what does it mean for the economy to be doing good, right? There's many different measures of the economy. Do we want to try to do things like exclude like weird times, like recessions, things like that, right? And so part of the point of this tool is that by switching around and trying many, many hypotheses, you can get this to go in almost any direction, right? So they're saying, so right now we're asking whether having more Democratic representatives is improving the economy along these three measures. Let's do this one maybe. So let's see. So if we do it this way, and let's take this off. So if we look at each dot here is a year, and the x-axis is how many Democratic representatives are in the House of Representatives. And you can see there's this positive correlation. When more Democrats are in office, there's a higher GDP, right? And we got a p-value of less than 0.01, which is great, right? But now let's say we flip this around. Let's say we want to try to show this for Republicans. We can do this too. We basically just have to pick some different indicators. So let's try, I mean, there's a few different ways to do this, but let's do, let's say like, right, so the more Republican governors that are in office, the better employment numbers are, right? Meaning the lower the unemployment rate is, right? And we got a nice small p-value here, right? And the idea here is that right, you can sort of, right, we can do lots of things to switch around this plot. You can see here our p-value, right? And what we can do is try to, if we're trying to push this p-value in one direction to the other, we can try to uncheck and check these boxes until we get it there, right? And so again, that right, the p-value, if we only report one p-value here from the version that worked in the way that we wanted it to, that's not really very useful, right? Because there's essentially many different hypotheses we're testing here. Okay, so let's do a quiz. So the question is, I'm going to give you 4 options here, and the question is, which of these does not suffer from multiple comparisons? A is testing a hypothesis at every location of the brain. B, testing a hypothesis in many subsets of subjects. C, testing a hypothesis on many different dependent measures. Or D, testing a hypothesis in a large data set. One does not. Okay, great. Yep, so the answer here is D, which is that testing a hypothesis in a big data set is not a multiple comparisons problem. Like the multiple here is about having multiple hypotheses. So testing a big data set, that's actually a good thing in general. Right, what we don't want to do is test lots of different hypotheses. So testing hypothesis at every location in the brain, right, that's essentially many hypotheses. Dividing up our subjects in many different ways is testing many hypotheses, and picking among dependent measures is testing many hypotheses. Again, we might want to actually, so like especially A here is something we might want to actually do. So we'll talk later on in the lecture about how we would go about that, right? But we can't just blindly do a separate statistical test and only report significant p-values. There's another issue I mentioned in my demo, which is called the file drawer problem, which is kind of related, but the file drawer problem is more about having multiple data sets instead of having multiple hypotheses. And so this figure is from a paper that was looking at studies of antidepressants. And so the first block here is showing all of the clinical trials that were run for this group of antidepressants. And you can see about half of them were negative and about half of them were positive, right? Meaning that about half of these trials are successful in showing some kind of group level effect of the drug. Then they looked at how many of these trials actually got published. And what they found is that there was a bias in publication, right? So the positive trials, all but one of them were published, whereas many of the negative clinical trials were not published. They also found that, so some of these dots here are, coming from the same trial where they had multiple outcome measures. So they might test both, measures of mood as well as measures of physical activity or something. And so what they found is that among studies that had both positive and negative results, right, they would tend to selectively report the ones that worked, the outcomes that worked, and not the ones that didn't. They also found that there would tend to be some spin, which was kind of like me complaining about the dirt on the dice or something, right? Some of these, the negative ones, they say, well, it didn't work because, something weird happened during the trial, so it's not really a fair test. And so, right, by this point, the literature is looking almost entirely positive. We're barely getting cited, right? So we end up, the state of the field, that this is what we're seeing in this last figure, which is that there's lots of studies reporting positive results. They're all getting highly cited, right? This looks super encouraging. This looks like this drug works really well, right? Almost everyone's having good outcomes. There were maybe a few weird things that didn't, but no one talks about those, right? And so the worry here is that, right, the sort of the thing that's closer to the real evidence in the real world is probably this thing on the left, right? Which is the actual outcomes, the actual raw outcomes of the clinical trials. But there's a lot of reasons why these results don't ever really make it out into the public knowledge of the field. And so again, there's a lot of questions about how we can make this better, right? How can we lose fewer of these studies and try to have a more accurate understanding of how these things are actually working? And so people have talked a lot about this. This is all like new stuff that people have just talked about in the past few years. And so there's still a lot of questions about which of these makes the most sense. Um, One idea, which I mentioned, is called pre-registration, which is that before you collect your data, you have to basically write down what you're going to do with it. So what kind of analysis are you going to do? Are you going to exclude any subjects? Right? Is dirt being on the dye going to be a reason to exclude that trial? Right? You have to write down exactly what you're going to do, how you're going to analyze it, what your hypothesis is. And then you submit this to one of these pre-registration servers, and there's a bunch of these. The U.S. government runs one as well, and so the idea is that then that your hypothesis is on this independent server with a timestamp of when you did it, and then you collect your data, and then you run your analysis on that data, right? And so now right, if you make any changes to your hypothesis or your analysis based on the way the data that came out, we can now figure that out, right? We can now compare what you actually did to the pre-registration. Of course, there's in real life, there's always some questions here about how much wiggle room people should have, right? Sometimes, like we've talked about in this class, sometimes which statistical test is appropriate to run might depend a little bit on the data. And so in some ways, we might need to leave some things unspecified. It might also be that we really want to collect 100 people, but then something there's some kind of unforeseen circumstance stopped us from collecting that many data, and so that much data, and so we now want to use a higher powered test than we were before, right? So there still needs to be some leniency about how we do this, but some kind of pre-registration is probably a good idea, right? It at least keeps us honest about what we thought before versus after we saw the data. There's also a more extreme version of this, which is called a registered report. So normally the publication process is that people design an experiment, they maybe pre-register their design, they collect their data, they do some analyses, they write up the paper, and then they submit this paper for publication to a journal. And the journal contacts reviewers who go through the paper and decide if they want to publish it in their journal or not. The idea with registered reports is that what you should do is design your study and then submit your study design to the journal. And so what happens is that the reviewers of that journal and the authors work together on the study design and until it's at a point where the reviewers say, this is a good experiment, it's well designed, the data that we're going to get out is going to be useful for telling us something about the thing that we're studying. And so the idea is that your paper is actually accepted before you start collecting data. And so the idea here is that the idea is that the way the data comes out is not really under your control, and we don't want to incentivize people to claim that there's a positive result in their data because that would be good for them, because they'd get a publication out of it. So the idea here is that the publication decisions are made only on the design of the experiment, and if the reviewers all say that the design looks good, then the paper is accepted. You just have to actually collect the data and report whatever the results are. This is, again, a pretty new thing. There's been right now there's a very small fraction of papers that go this route, but I think it is an interesting idea to try to move around the incentives a little bit so that the real work should be in the design of the experiment and the design of the analyses. And we shouldn't sort of punish people if the results don't come out the way we expected. Right? That's still useful knowledge for the field to have. And we don't want to have this file drawer problem of blocking papers that are showing negative results. Another kind of movement in the field has been to do better sharing of both our data and our code. And so this means sharing our raw data in some public way, as well as sharing the analysis code that we used. There's even more extreme versions of this that involve actually sort of constructing an entire encapsulated virtual machine that runs all of our code using the right versions of the software and things like that. And so this is good because it's, first of all, a little more transparent about how your result was achieved, right? And so it shows the hypotheses that you're actually testing in your code. There's lots of other benefits to this too, right? So sharing data means that other researchers can reuse your data, which is becoming a lot more popular in psychology and in neuroimaging. Um, and sharing this code also lets other people, right, see the details of what you did and potentially use your code on other data sets, right? So this is another direction here, is that one way to guarantee that multiple comparisons isn't happening is to replicate some experiment, right? So maybe we did peek at our data a little bit when we were making our hypothesis here. But then what we can do is just like lock in that hypothesis, collect a brand new set of data, and see whether the hypothesis still works, right? The idea here in statistics language, right, is that we're getting a new sample from our population. And so if we take two samples from our population, they should only be similar to each other in the ways that the population actually has real features, right? So any sample we get is going to have some weird idiosyncratic sample specific stuff. But if we develop a hypothesis on one sample and then it works on a new sample from the population, that's good evidence that we're really saying something about the population here, and we didn't just like fine tune our hypothesis to the weirdness of this particular sample. Okay, so another thing that we may want to do is that sometimes we purposefully want to conduct multiple comparisons. And so there's a number of ways this comes up. So one I mentioned is like in neuroimaging. So my lab does a lot of fMRI, and we may want to ask whether we have some idea about something the brain might be doing, but we don't know which part of the brain is doing it. And so what we want to do is test our model at every single location in the brain. Right, and for the scans we use, we get maybe 50,000 different locations in the brain where we get data, right? So we want to test 50,000 hypotheses for each. We want to test one of these for each location in the brain. Also, another thing that's come up over the past couple of weeks is when we run an ANOVA, if the ANOVA tells us that there's some relationship between the group label and our outcome measure, it doesn't tell us which of the groups is driving that result, right? It could be that all the groups are different, or maybe just one of them is different. And so we want to do some kind of hypothesis test where we want to test, like, is group 1 different from 2? Is 1 different from 3? Is 2 different from 3? Right? We want to ask all of these questions about which groups are different from each other. Right, but then we have to think here about what's gonna if we just do this blindly, what's gonna happen to our error rate, right? If we just do all these multiple comparisons tests, how bad are things gonna get? So if we repeatedly test the same data in different ways, meaning we're applying lots of different hypotheses, the overall odds of us getting a positive result are going up, right? Because we're running many different tests. And if we get a false positive in at least one of those tests, then we'll get an overall false positive. And so I'm going to call this the family-wise error rate. Again, some people would call this a type 1 error rate. I don't like to use that terminology, but this is the overall false positive rate for this entire family of tests. So we're running lots of different hypotheses, and we're asking what's the chance that we're going to get a false positive overall in this whole set of hypotheses, right? So if we are testing our model at all 50,000 locations in the brain, and we want to say, right, is there any evidence for the model anywhere? This family-wise false positive rate is the chance that we're going to incorrectly say that any location in the brain is doing something that it's not. In the textbook, they call this the experiment-wise error rate, because they're basically thinking of within a single experiment, you're running many hypotheses. But this term is kind of weird because, first of all, the problem's not limited to experiments. This is also true of observational data. And it's also doesn't have to be within a single experiment. This can also happen if, for example, many different researchers are using the same data set and testing different hypotheses on it. So there's, again, some debate about what like the right way to define families is here, but the idea is that any data that is coming from the same sample in some way, we have to be a little bit careful that if we're running many tests on it, right? Because this family-wise error rate, the chance of a false positive is going to go up the more hypotheses we run. Okay, so I'm about to ask a quiz question. I'm just going to set up the question first. This is one of the harder quiz questions, so I'm just giving you a heads up to start thinking about it. Um, so here's the situation. So we have a standard normal population, and I'm going to sample groups of 10 numbers. So I'm going to grab 10 numbers. They're going to be group A. I'm going to grab 10 new numbers. They're going to be group B, and so on, right? So I have these 50 groups, 10 numbers each. They're all sampled from this standard normal distribution. Okay, now what we're going to do is we're going to look to see if any of these samples are coming from populations with different means, right? Where what we're going to do is we're going to run this independent samples t-test on every single pair of groups. So that's 1,225 tests total, right? I'm going to compare group 1 and 2, 1 and 3, all the way up to 1 to 50, 2 to 50, right? All of these pairs. Now the null is true here because I took all these samples from the same exact population. There's no difference in the population mean that these samples are coming from, right? And so if I get any p below 0.05, that's going to be a false positive, right? And so the question here is, what kind of p-values are we going to get? So we're running 1,225 tests. Each of those tests, every single one of those t-tests is going to pop out a p-value, right? And here the null is true, right? So the question is, if the null is, are they all going to be like clustered around 1? So they're going to be relatively high. They're going to be somewhere around 0.5. They're going to be somewhere around 0, or they're just going to be totally random between 0 and 1. All right, so I'll give you a little time to think about this, right? The question is, if we're running these these t-tests between pairs of groups, and all of the groups are actually sampled from the null, they're all sampled from the same population, what will the p-values look like in that case? All right, what do people think? Yeah, don't be afraid to guess. This is a pretty hard question that I definitely did not know when I took intro stats. Yeah, so there's a guess of A, which would make sense because, right, p-values close to 1 mean that there's very little evidence against the null, right? So that wouldn't make sense because the null here is actually true, right? So yeah, I see some A's, some D's, and lots of question marks, which is good because it's not super clear. So on the next slide, I'm gonna actually run this, right? And so I just simulated this in R. So along the bottom is our 1,225 tests. And on the y-axis, I'm going to plot the p-value of each of those tests. And this is what it looks like, right? So what's happening here is that we're just getting p-values that are uniformly distributed between 0 and 1. You can see there's like a little bit of weird, like, so the way I'm doing the tests here, they're a little bit ordered, which is why there's some weird clustering in the data, right? But we in general are getting values uniformly between 0 and 1. And so so the fact that we're getting these uniform p-values under the null hypothesis, this is actually like what the definition of a p-value is, right? I think we don't usually talk about it this way, but right, what a p-value is, when we say a p-value of 0.05, for example, right, that means that if the null is true, it'll only produce a p-value of 0.05% of the time. Right, you'll only get a p-value less than or equal to 0.05% of the time. If the null is true, you'll only produce a p-value less than 0.25% of the 25% of the time, right? 0.25 of the time, right? So, what a p-value, right? Under the if the null is true, then our p-values will be uniformly distributed between 0 and 1, right? Which means, for example, that if the null is true, then we will sometimes get p-values that are less than 0.05, right? And in fact, it'll be about 5% of the time we're going to get significant p-values, right? In this case, it actually worked out to like a little bit more. It's just random on different runs, right? But um, so right, so we should if we're looking at right whenever we're getting a p-value, we're sort of comparing it to this uniform distribution and asking, is it likely that the null hypothesis could have produced this p-value or not? Right, so yeah, so when the null is true, our p-values will be uniformly distributed between 0 and 1. Right, and so if we only run a single test, which is what we've been talking about for the whole year, the whole course so far, is that if we get a p-value less than 0.05, then what that tells us is that it would be relatively hard for the null hypothesis to have generated that p-value, right? It's not impossible, right? It can do it, right? All the blue dots there are times that it's doing it. But it can only do it like 5% of the time, right? And so that's evidence against the null being true, because usually the null hypothesis isn't going to give you small p-values. The problem is that if we run, say, 1,000 tests and we get one of them with a p of less than 0.05, that's totally not impressive, right? Because we'd expect about 5% or 50 in this case of the tests to be false positives, right? And so so getting a p less than 0.05, in this case we're running many tests, right, doesn't actually tell us anything interesting about the null, right? The null is going to be generating many false positives here too. Okay, so how can we try to fix it? Like I said, there are cases where we want to run lots of hypotheses, right? Maybe even more than 1,000, maybe tens of thousands. So what can we do? So the simplest thing we could do, which is called Bonferroni correction, or alpha. And so the Bonferroni correction is, what we do is we take the number of tests, C, and we just divide our threshold by that number. So if alpha is 0.05, for example, and we are performing 100 hypotheses, then what we're going to do is we're only going to say that one of those hypotheses is significant if it passes this very restrictive threshold of 0.0005, right? We need to get a p-value below 0.0005. So this is pretty simple, right? And the intuition of this hopefully makes sense, right? Which is that if we're running more tests, if we want an overall family-wise error rate of 0.05, right? So we want only a 5% chance of saying that any of these are false positives. We need to be really conservative for each test, right? We need to, basically what we want is that if overall the number of false positives can't be more than 5%, we can't let any individual test have a large chance of producing a false positive, right? So so this is a pretty simple idea, right? We're just going to lower our alpha thresholds way down. The problem is that this is usually like not practically doable, right? To get a p-value less than 0.0005 is just probably it would require like millions of dollars for a neuroimaging experiment, for example. I mean, maybe even more than that. Like getting the problem here is that these are extremely conservative thresholds. You need very high powered hypothesis data sets to be able to answer these questions. So if you're only testing a small number of tests, then this is fine. So, right, if you're testing like 3 different outcome measures, you can just divide 0.05 by 3, and that's doable. The problem is that, right, once you get into like hundreds or thousands of tests, this doesn't work. So, okay, so there's another, so I should say too, there's like a whole family of approaches here. That the most common approach we use in neuroimaging, actually I'm not even going to talk about today, which has to do with redefining the kind of error rate that we want to find. So we don't use this family-wise error rate, we use something else. But so one thing we can do in this family-wise domain is this what's called a step-down procedure. And so the idea here is we're going to use this super conservative Bonferroni correction only for one of the tests, and then we're going to gradually relax this criterion, right? And the idea here is that we don't actually have to be so conservative with every single test, that if there's at least some of the tests that seem like they're passing this threshold, we can be more liberal on the other ones. So I'm going to show how to apply this procedure for ANOVA results. So the idea here is that we have some ANOVA test where we are trying to figure out whether there's some relationship between group labels and some outcome. But then what we want to do is figure out which of these groups is actually driving this result. So what we're going to do is, in addition to an ANOVA, we're actually going to also use some t-tests, and we're going to make use of this Bonferroni correction with this step-down procedure. Okay, so here's how this works. It's relatively simple. So we first perform our overall omnibus ANOVA to ask, is there any significant relationship between the group labels and the outcome? If the ANOVA says no, so if the p-value is above our threshold of 0.05, then we just stop. If the ANOVA is significant, then we're going to continue. So what we're going to do is perform all pairwise t-tests between every pair of groups. So if we have 3 groups, for example, this would mean doing a t-test between group 1 and 2, 2 and 3, and 1 and 3. If we have 4 groups, right, then we'd be doing like, I guess 6 tests, right? 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. So we run all these tests, we get a p-value from each of them, and C is the total number of tests that we're running. Then what we do is we sort our p-values from smallest to biggest. So the smallest p-value here, right, are the groups that are looking the most different, right? Where their difference between the means is the most different from the null of 0. And what we do is we take our lowest p-value, so our smallest p-value, and compare it to this criterion of alpha over C. So if we're using an alpha of 0.05, we take 0.05 divided by the number of t-tests we did and see whether our p-value passes that threshold. If it does, then we label that first comparison as significant. We say that there is a difference between those 2 groups. And then we look at the second lowest p-value, and we compare this second lowest p-value to a slightly relaxed threshold, which is alpha divided by the number of tests minus 1. Right, so this is going to be a bigger number. We're making the denominator smaller in our criterion, so this threshold is going to get bigger. And we're going to compare the second lowest p-value to this slightly relaxed threshold. And if this is significant, then we say, okay, those 2 groups are also different. And then we keep going like this, right? We keep subtracting 1 from the denominator. We keep relaxing this threshold a little bit, comparing our p-values against this slowly relaxing threshold. As soon as any of our p-values fail, as soon as we get to a p-value that doesn't meet the current level of the threshold, then we just stop. We don't test anything else, right? Then we just stop our tests. All the other groups, we say that we can't reject. We don't know whether to reject the null or not, right? We don't reject the null. We don't know whether the null is true or not for the other groups. Okay, so let's do an example of this. So we're going to pull back up this ANOVA data with the green, red, blue groups. So if you remember, right, the first step of the step-down procedure is running our ANOVA, and we ran the ANOVA on this and got a significant result. So we're allowed to proceed, meaning that there is some relationship between the colors and the means here. And so we're going to start running t-tests. Here we're using equal variance 2-sample t-tests. Again, if the groups have different variances, you could also use a different unequal variance 2-sample t-test. So we run our t-tests between the groups, and there's 3 tests we're running, right? We're comparing every pair of the blue, red, and green groups, and we're getting a p-value for each of these outcomes. The next step in the procedure is sort the p-values. So, right, the smallest p-value is between blue and green, then between blue and red, then between red and green. Okay, so C is 3 here, right? It's not because there's 3 groups, it's because there's 3 pairs of groups, right? So we ran 3 t-tests here, and so C equals 3. And so we're going to compare our lowest p-value to the Bonferroni correction, which is 0.05 divided by 3, which is 0.017. And our p-value is lower than that. And so we reject the null hypothesis, right? Meaning that we say, okay, blue and green, these groups have different means. Then we look at our next p-value, which is 0.00039. We're going to compare that to a slightly relaxed threshold. Now we're only dividing by 2 instead of 3. Our p-value passes that threshold, so we reject the null hypothesis, meaning we say these blue and red groups have different means. Then we get to our last test here. We're comparing it against our fully relaxed criterion. You can see their criterion now actually has relaxed all the way back up to just a regular 0.05, but we don't make it under that bar, so we fail to reject, right? Meaning that we don't have strong evidence for red and green having different means in this data set. Right? If there were more tests to run, we wouldn't run them, right? As soon as we get a fail to reject, we just stop, and all the other comparisons, we just say we don't have evidence that they're different, right? So we conclude that blue and green are different. We conclude that blue and red are different, but we don't have evidence that red and green are detectably different in this data set. So this is effective. It's still somewhat conservative, but this is at least one approach that people do use. It's somewhat conservative in the sense that this limits the overall family-wise error rate to probably a little bit less than 0.05, right? But that's okay. We'd rather be a little conservative on these tests. It's also practical. Like, this is one of the only multiple comparisons corrections you can actually do by hand. A lot of the other ones are really complicated that basically you need software to run for you. And I've been I think I've mentioned before, these kinds of tests are called post hoc tests, meaning that they're after our like real test, right? In this case, the real test we're running is the ANOVA. And then this is a post hoc test, meaning that it's just trying to figure out why the ANOVA gave us the result that it did. There's other kinds of post hoc tests that people use with ANOVAs as well, that they have this same kind of flavor. You might see this particular procedure, you might see referred to as like a home Bonferroni test. And just due to the people that developed this, right, this is basically sort of a relaxed version of like a Bonferroni or a SIDAC test. Okay, let's do a quiz for this section. So this step down procedure, we're using it to determine whether our ANOVA result was a false negative, which group differences are driving our ANOVA result, whether our ANOVA assumptions were properly satisfied, or whether our ANOVA result was a false positive. All right, what do we think? Right. I see a lot of people on the D train, but so the step down procedure doesn't tell us anything about whether ANOVA results are wrong or not, right? So it's not A or D here. The step down procedure runs the ANOVA first, and then whatever the ANOVA decides, if the ANOVA decides to reject the null hypothesis, then that's what we're assuming for the step down procedure, right? If the ANOVA says that there's some difference between the groups and the outcome, we trust it. And so, so I see people now switching over to B, which is right. So, right, what this is telling us is we're trying to figure out why we got that positive result in the ANOVA, right? We're not questioning the ANOVA result. We're just trying to figure out, can we say which group or which pairs of groups are actually driving this ANOVA result, right? And so, so this is, again, this is another reason we call this a post hoc test, is it's sort of after our main statistical test that's actually telling us whether there's some group related influence on these outcomes or not. It's just a way of trying to dig into the model a little bit to figure out which of these pairs of groups are causing differences. Right. And we have to be a little careful. We wouldn't want to do these pairwise t-tests first, because that would be right, then we run into this multiple comparisons problem. And so we just do this after we get a positive significant ANOVA result to see, can we say which groups are doing this? And so it's not like we're actually not guaranteed that any of the groups will show a significant difference in the step down procedure. So it's possible to get a significant ANOVA result, but our step down procedure just like fails immediately on the first step here, right? So this very first p-value we try doesn't pass our threshold, right? So that's totally possible. It doesn't mean that the ANOVA was wrong. It just means that we can't actually figure out um, which pairs of groups are driving this difference, right? So it could be that um, all of the groups are kind of like borderline different from each other. So we can't actually say with confidence whether any pair of them is different. But the ANOVA can tell us with confidence that there's something going on. There's some relationship between the group levels and the outcomes, even if we can't detect which pairs of groups are driving it. Okay. So yeah, so again, this is a sort of like practically useful thing for just trying to figure out what's driving our ANOVA effects. It uses this threshold that's not quite a Bonferroni one because it's relaxing over time, right? But it's still quite conservative, and so we might miss real effects here. You can also note in the example that we did that these things are not like transitive. So right, what we ended up showing here was that blue and green are different, and blue and red are different, but we weren't sure about red and green, right? And so if you look back at the original data here, oops, right, this is what the data looks like. And so what we said is that blue is different from red and blue is different from green, but we weren't able to say whether red and green are different, right? And so we can have sort of all different combinations of these differences. And it's just telling us about what we have the power to detect. It's not necessarily telling us that red and green are actually the same. We would need to use other kinds of statistical techniques to make that kind of claim. Okay. So the last topic I want to talk about is data peaking. And so this data peaking, I think, is one of the more like insidious ones that you really could think you're doing things the right way and still run into massive false positive problems. So one version of the data peaking problem goes like this: is we're running an experiment and we don't really know how big of an effect size to expect. We're not really sure how many people we're actually going to need in order to get significant results. So what we're going to do is we'll start by just collecting a few people, like 10, and then we're going to just keep collecting people until we get a significant result, right? And then running each person costs time and it costs money, right? Both in terms of the researcher that's running it as well as we're paying people for these. And so one way to maybe like try to be efficient is let's just run people until we get a significant result and then stop, right? We don't need to keep running people after that point. We've already seen that there's a difference. So I think this sounds kind of reasonable. And I mean, in practice, this often is how experiments end up getting run, is that, right, you run some people and if things kind of look unclear, maybe we run some more people, right? The problem is that this is actually bad. This is actually doing a kind of like file drawer or multiple hypothesis kind of thing where we're basically doing lots of hypothesis tests, right? So what the plot here is showing is we just right, what's like our stopping size, what's like the most number of people we'd be willing to run. And if we use this procedure with a relatively large stopping size, we can actually get false positives very frequently. So if we say we're going to run up to 100 people, stopping whenever we get a significant result, even if the data is null, we can still about like 30% of the time get a significant result, right? And the problem is that because the p-values are uniformly distributed when the null is true, that means that they kind of wander around a little bit randomly, right? As we're collecting new data, the p-value is kind of like wandering up and down if the data is null, right? If the null hypothesis is true. And so because of that, if we just wait for it to get under 0.05 and then stop, right, then like about 30% of the time we'll be able to do that, right? These wandering p-values will go below our threshold and then we'll stop data collection, right? So this is bad, right? So we don't want, this is another version of kind of like picking our data set to match our hypothesis, right? Which is that we keep checking our data set and as soon as it looks good, we stop and don't risk adding more people that might disprove our hypothesis, right? So this is not good. So there's one question here about how do we, so one option is we have to ahead of time specify how many people we're going to collect, and we can look at the data if we want, but we promise to collect that many people and analyze that whole data set. And so we're going to talk, I think, maybe next week or the week after about that, which is we can use this approach called power analysis to try to figure out how many people we're going to need. If we know something about how hard this effect is to find, we can make a guess as to how many people we need. So that's one approach, is we pick the number of subjects before we start running. Another approach is we do peek at our data, but we use some kind of different threshold. So one option, for example, this is the kind of similar to like a Bonferroni thing, is that if we are doing lots of peaking, we have to be more conservative. So if we want an overall false positive rate of 0.05, then if we're making lots of peaks, we need to actually drop our alpha threshold for each of those tests. So if we're peaking like 8 times, we need to look for p-values that are less than 0.01 if we want an overall false positive rate of 5%. This is one option. Another option is that we actually have our alpha bounds change with the amount of data that we collect, meaning that as we collect more data, these alpha bounds are getting smaller. And so at least the first version of this was from Abraham Wald, who we saw back when we were talking about survivorship bias, right? He was one of the people that was working at Columbia for the government during World War II. And this is actually what he's more famous for. The survivorship bias is one thing he worked on. This sequential test was another thing that he worked on, which is that as we're monitoring production from factories, for example, we want to be able to take lots of samples and then say if we want to be able to figure out how many samples we need to collect to be able to figure out if this particular lot of things that we're producing from this factory, which at the time, right, they were mainly concerned about things that they needed for the war. And we want to be able to figure out, can we say that this lot is good or bad? And so he had this kind of sequential test that works like this, which is that basically as you collect information, you're sort of going along this lines here where, so anytime you find something bad in your lot, you go up. Anytime you find something good in your lot, you move horizontally here, right? And so what happens is that as you're going, there are these bounds that are moving that tell you to either accept or reject what you're finding. And so we keep taking samples from this lot. If we ever get above this line, then we reject it. We say there was too much bad stuff in this lot is not conforming to our standards. If you ever make it past this line, then we accept the lot, meaning that we found enough good stuff in this lot. It seems like it's fine, right? We expect some failure rate of our samples, but this was an acceptable failure rate. So yeah, the idea here is that these bounds kind of move with the amount of data you collect. So as you collect more data, you're able to sort of detect smaller differences. And it accounts for this fact that you're continuously sampling and continuously trying to make a decision. Right. And so again, this is, as with many things in statistics, this was something that was developed to solve this very practical problem, which is we need to make a decision as quickly as possible when we're producing these things from these factories about whether it's working or not. Right. We don't want to just say, we're going to produce 100 units and then check then. We want to know as we're producing if we can say that something's going wrong or not. Right. And so, so this was a lot of Abraham Wald's work was figuring this out of how do we have a test that we can be constantly checking in a way that's not going to give us lots of false positives, right? A false positive here would mean that we're throwing away lots that are actually good. Okay, so yes, so just to sum up, and again, feel free to ask any other questions as I'm going through this summary. So, right, we have this family-wise, either type 1 or family-wise false positive error rate that is talking about the chance of making at least one false positive error across many analyses. And the main reason that we used our ANOVA, for example, is that it's a single omnibus test that doesn't suffer from this multiple comparisons problem. But we still might want to do all these pairwise comparisons in order to get more information about what's driving our results, right? And so we can use these kinds of post hoc tests. So the one we talked about, the only one that you'll be asked to actually do is the step down procedure, which is again a little conservative, but pretty general and relatively easy to use multiple comparisons correction. There's many other ones that right? Many of them are based around this idea that the p-values should be uniformly distributed if the null is true, and we look to see if the p-values in all of these pairwise tests look like they're coming from that uniform distribution or not. All right, any last questions? All right, great. So there's a lab today that's based on the material from today and Tuesday's lectures and last Tuesday's lectures 2 days ago. Yeah, please get started on project 3 before the weekend if you haven't already. And yeah, there's also again homework, next homework that's due next week. All right. Yeah, and again, feel free to email me if you have any questions or if you need extensions for the project. All right, I'll see everyone next week.